The world can feel, well, completely random a lot of the time, right? But what if I told you there's a hidden order to it all? A kind of mathematical language that helps us make sense of the unknown. Today, we're going to start unlocking that science of uncertainty.
We deal with this stuff every single day. Just think about it for a second. You check the weather forecast, and what does it say? A 30% chance of rain. That's it. That's probability right there in action. It's just a simple number that helps us navigate a world that we can't predict with, total certainty.
And it goes way beyond just the weather. From that lottery ticket you might buy to the bigger risks we all take in life. We're constantly, instinctively, trying to size up our chances. But how do you actually measure something as fuzzy as chance? For that, we need a specific tool.
And that tool, you guessed it, is probability. At its absolute core, it's just a way to put a number on how likely something is to happen. It gives us a scale, a way to measure uncertainty, turning a vague gut feeling into a solid, concrete number we can work with.
So, let's look at our scale. On one end, at the very bottom, we have 0. This means an event is absolutely, completely impossible. No way, no how. It is never, ever going to happen.
Then, right smack in the middle, we've got 0.5, or 50%. This is a perfectly even chance. The classic example, of course, is a fair coin flip. It's just as likely to land on heads as it is to land on tails, 50-50.
And all the way at the other end of the scale is 1 or 100%. This represents total, absolute certainty. An event with a probability of 1 is guaranteed. It's gonna happen. For instance, the sun will rise tomorrow. That's a certainty.
Okay, so we've got this scale, right? From impossible at 0 to certain at 1. But how do we actually decide where an event falls on that scale? Well, it turns out there are two main schools of thought here. One is based on pure theory, and the other is all about real-world experiments.
So the first approach, we call it classical probability. It's all about logic. It happens in your head. You look at all the possibilities in a perfect system. With a fair six-sided die, you just know there are 6 equally likely outcomes, so the probability of rolling a 4 has to be 1 out of 6. Easy. But the second approach, the frequentist view, is about getting your hands dirty. It says, forget theory, let's just run an experiment. Instead of assuming the coin is fair, you're going to flip it thousands of times and just see what happens.
And this is such a powerful idea. I mean, if you flip a coin just 10 times, you might get 7 heads. That's kind of weird, but possible. But if you flip it 100,000 times, the number of heads is going to be incredibly close to 50,000. It's almost a law of nature. The more you repeat the experiment, the closer your results get to the true hidden probability.
All right, so far we've been talking about single events, one coin flip, one roll of the dice. But here's where the real magic begins. It's when we zoom out and start to map the probabilities of every single possible outcome all at once. This is how we start to see the big picture. Let's imagine we go to a bus stop and we just start recording how long people have to wait for the bus. We collect all this data and, well, right now it just looks like a table of numbers. It's messy, it's kind of hard to see any real meaning in there just yet, isn't it? But then, when we plot that data, something amazing happens. A shape starts to emerge from the noise. All of a sudden, we can see it clear as day. Short waits are really common, while those super long waits are much, much rarer. We've just transformed a messy table of numbers into a clear visual pattern. And this shape, this pattern, has a name. It's called a probability distribution. You can think of it like a complete map of chance for a random event. It doesn't just give you one number, it shows you the entire landscape, what's likely, what's unlikely, and absolutely everything in between.
And here's where it gets really fascinating. It turns out that nature kind of has a favorite shape. There's one particular probability distribution that shows up so often in so many different places that scientists actually call it the normal distribution. You probably know it by its more famous name, the bell curve.
Seriously, this thing is everywhere. From people's heights, to tiny errors in measurements, to the weight of cereal in a box, this symmetrical, beautiful, bell-shaped pattern is one of nature's favorite designs. It describes countless things in the world all around us.
Now, the bell curve has this predictable secret code, often called the empirical rule. It uses a concept called standard deviation. Just think of that as a standard-sized step away from the average. And the first part of the code is this. For any bell curve, about 68% of all the data, the huge majority, is found within just one of those steps from the center.
So what happens if we take 2 steps out from the average in either direction? Well, now we've captured even more. We've now accounted for about 95% of all the possible outcomes. You can see how getting a result that's far from the average is starting to get pretty unlikely pretty fast.
And if you go out 3 of those standard steps, you've now captured 99.7% of all possible outcomes. This is incredibly powerful. It means that anything that falls outside of this range, well, it isn't just unusual, it's a genuine statistical outlier. It gives us a really clear line between what's expected and what's extraordinary.
So, okay, we get it. It's a pretty shape. But what's the point? The real power of the bell curve isn't just admiring its form, it's using it as a practical tool to make predictions and really smart decisions.
And to do that, we use this really clever tool called a z-score. Forget the formula for a second and just think of it like this. The z-score is a universal yardstick. It tells you exactly how normal or how weird any single data point is by measuring how many of those standard steps it is away from the average. It lets you compare apples and oranges.
So here's how it works in the real world. Say a machine is trying to put 500 grams of cereal in every box. What's the chance a box gets underfilled at 490 grams? Well, first we use our z-score yardstick to measure how far away 490 is from that 500-gram average. And that score, that z-score, points us to an exact probability. This isn't just some abstract math problem. This is literally the foundation of modern quality control.
So, let's step back. We've gone from asking simple questions about rain all the way to uncovering one of the most fundamental patterns in the entire universe. It really is a completely new way of looking at data and at uncertainty itself.
And the crucial point is this. Probability isn't a crystal ball. It doesn't predict the future. What it is a lens. It's a lens for understanding the present. It lets us see the hidden, predictable order that governs so many things that on the surface just seem totally random.
The amazing thing is, the bell curve is absolutely everywhere once you know what to look for. So the real question is, now that you have this lens, now that you know the secret, what hidden patterns will you start seeing in the world around you?